my name is Mark Barrett and I'm a Senior Research Development Engineer from the Solid State Pharmaceutical Cluster within Ireland. I'd like to welcome you all here today for the first part of a two-part webinar series on the optimization and scale-up of an anti-solvent addition crystallization. The Solid State Pharmaceutical Cluster aims to support the pharmaceutical manufacturing, commercialization and research industry in Ireland through collaborative research projects, upskilling and training programs. The academic partners within the cluster bring a wide range of expertise from solid-state material science to organic chemistry to the optimization and scale-up of crystallization processes through PAT. This is greatly complemented by our wide range of industrial partners who bring a huge range of expertise and experience from pharmaceutical manufacturing, commercialization and research. More information on the cluster can be found on the website below. The work presented during this webinar series will focus on the work produced during my thesis from the UCD Crystallization Research Group on the optimization and scale-up of an anti-solvent addition crystallization, titled From Lab to Pilot Plant. So typically this work looks at the challenges R&D chemists and engineers face in the pharmaceutical industry during the development and optimization and scale-up stages of crystallization development. The first part of this webinar series will look at the optimization protocol developed at the bench scale. So the scope of this study was the combination of in situ PAT analytics with computational modeling software packages. So we used focus beam reflectance measurement, or FBRM, to characterize particulate nucleation and growth, agglomeration, secondary nucleation, etc. We combined this technology with PVM to heighten our understanding of the attained in situ particle morphology, also agglomeration, oiling out and attrition. We used mid-IOR to quantitatively describe our in situ supersaturation as a function of time, and finally we used computational fluid dynamics to gain an understanding of the turbulent mixing present within all scale of crystallization vessels assessed. So we call this the scale-up toolbox. So the objective being to use the scale-up toolbox to optimize a bench scale crystallization within the lab. That is a crystallization that is both efficient, repeatable and one that is suitable for manufacturing scale-up. So finally, the overall objective was to reproduce a chord length distribution outputted by the FBRM from an optimized 500 ml experiment at the 2 litre and 100 litre scales. We also developed protocols to reproduce this chord length distribution in a scale down environment. So taking a look here at our presentation overview. So many of the attendees, if not all, know a tremendous amount about why anti-solvent systems are challenging to scale up. So I'll just briefly touch on this topic as an introduction. We'll then go through the methodology used to characterize the metastable zone and some case studies on the optimization of this process. Finally, then to some conclusions. So initially, let's look at why anti-solvent systems present challenges on scale-up. So to gain an insight to why anti-solvent and reactive systems are very challenging to scale up, we must first look at the different scales of turbulent mixing. So at the scale of the tank, we have the macro mixing time scale, or the blend time. So within the lab, this could be maybe a half or 1 second, and on scale up to manufacturing scale, this could be 15 or 20 seconds. At the intermediate scale of mixing, we have meso-mixing that can be both a function of the scale of the tank, but importantly, it can also be a function of the scale of the feed pipe. Then at the finer scale of mixing, we have micro-mixing, greatly defined by Baldiga and Bohr many years ago. So within the literature and within our research group, the effect of these turbulent mixing timescales on the nucleation or metastable zone width, growth and nucleation kinetics, polymorphic form, seed dispersion, reaction and heat transfer kinetics has all been identified. So we really want to use these turbulent mixing timescales to heighten our understanding of our anti-solvent system. So just introducing the classic equations here for crystal nucleation and crystal growth. The point being just to show that obviously we all know that supersaturation can dictate both nucleation and growth. But importantly for anti-solvent systems, crystal nucleation can really be exacerbated by the introduction of problematic supersaturation gradients throughout your vessel. So taking a look here at these tracer clips, firstly at the 500 ml scale, we can see that the introduction of this tracer shows that the system is extremely homogeneous and that the system is in turn well mixed. So if we take this system and then scale up to our pilot scale crystallization vessel, we can see the immediate introduction of problematic supersaturation gradients to our vessel. So obviously the exacerbation of these turbulent mixing timescales that I showed on the previous slide facilitate this introduction of supersaturation gradients. Now, these can be problematic as they can affect your purity, particle size, or if oiling out is an issue, even your yield. So it's important to really forge the gap between these two scales by developing protocols and methodologies to ensure we never observe these problems. So now looking again just at our presentation overview, and we'll just jump on to some characterization work of our metastable zone and our first case study. So the system we worked with was benzoic acid, so it's a non-polymorphic system obviously, and our solvent was ethanol and our anti-solvent was water. Des O'Grady, a previous colleague of mine from the research group, performed detailed solubility and kinetic work with benzoic acid as an anti-solvent system using mid-IOR and FBRM. So I'll touch on some of his work throughout this presentation. So we characterize our solubility on an anti-solvent free basis. So all that means is our y-axis, which is solute concentration, is in grams of solute per gram of solvent, not gram of anti-solvent. And then on our x-axis we just have gram of anti-solvent per gram of solvent. So this just graphically allows us to have a nice linear addition. When we're undersaturated, we keep adding our water till we pinpoint nucleation by FBRM. We now have a metastable zone with, and we also have a supersaturation at the time of nucleation. So I guess from this sort of graphical method we can easily obtain our metastable zone with on this anti-solvent free basis. Shown here is the vessel schematic used for all experimental and computational fluid dynamic work. Just to note here, point 1, which is a common industrial feed point location found by the reactor wall. This is initially where all computational and experimental work was done. So now looking at case study 1, the importance of anti-solvent feed location in achieving a robust scalable crystallization. So throughout the literature and within the UCD Crystallization research group, the effective process parameters such as agitation, add rate, addition location and scale on the metastable zone width or the nucleation point has been identified. So now let's look at this a bit more carefully for anti-solvent systems. So looking now at the metastable zone width as a function of anti-solvent addition rate and this far feed point close to our reactor wall and above the surface. So now with our metastable zone width on the y-axis and our addition rate on the x-axis, we can see at low addition rates between 0.05 and 0.15 grams per second, we in fact produce a repeatable nucleation event over the course of 3 experiments. However, between addition rates of 0.25 and 0.5 grams per second, this correlation of increasing metastable zone with increasing addition rate actually deteriorates, and we actually observe premature nucleation. So premature nucleation is in fact the observation of solids by FBRM prior to the bulk solution being supersaturated. So we can say for this process that the premature and inconsistent nucleation events really mean that this process is undesirable for scale-up. So this was the birth of CFD, to really understand the effect of turbulent mixing at this sort of common industrial feed point location. So the following is a cross-section, a computational fluid dynamics cross-section of our 500 ml bench scale crystallization vessel. So you can see our temperature probe and our upward pumping pitch blade. What we're showing here are simply velocities in the Z component, that is velocities in the upward or downward direction. So blue velocities being downward and red velocities being upward. So the following annotation really sort of explains the axial flow present in this vessel. So as we can see, the far feed point is located in a region of upward pumping velocities created by the upward pumping pitch blade impeller. So now we sort of have an appreciation that there is numerous different mixing environments throughout the vessel. So we now want to qualitatively describe the dispersion of supersaturation from this feed point. So these are computational fluid dynamic tracer clips that we will use to qualitatively describe the diffusion of supersaturation from our feed point. If we look here on the right, we can look at our liquid surface, and we can observe that the supersaturation when released from our feed point actually lingers at the liquid surface. So we can say there's a delay in entrainment of concentration to the bulk. This is verified by the front cross-section tracer clip, which really shows the sort of hold-up due to the upward pumping action of the pitch blade impeller at the liquid surface. This in turn can facilitate an increase in concentration at the liquid surface, which in turn can facilitate this reduction in metastable zone. So we want to use these sort of visual aids now to quantitatively describe this inconsistent and premature nucleation. So let's now apply those turbulent mixing timescale equations I introduced at the start of the webinar to our computational fluid dynamic models to understand what is dominating the diffusion of concentration from our feed point. So from this analysis, the intermediate scale, mesomixing, by means of turbulent diffusion induces premature nucleation. So this plot is a plot of mesomixing by turbulent diffusion on our y-axis and addition rate on our x-axis. So we can see at low anti-solvent addition rates we have a reduction in our mesomixing timescale. So in fact this facilitates conditions for a repeatable crystallization over the course of 3 experiments. However, above this defined threshold we actually induce premature nucleation. So we now in fact have a scalable number which we can take to a scale down environment or a scale up environment to ensure we never induce premature or excessive nucleation events again. So I define here that the increase in time to diffuse supersaturation from the feed point facilitates the conditions necessary to prematurely nucleate our solute. So now let's use CFD to optimize our ad location. So an optimal anti-solvent feed point would be one that's in an environment of minimal meso and micro mixing timescales. So now let's use CFD to produce a contoured plot of these timescales at the liquid surface. As shown, this is the CFD contoured plot for micromixing at the liquid surface. Straight away we can see that our current feed point location by the reactor wall is in fact located in a region of poor or long micromixing values, which contribute to poor diffusion of supersaturation from the feed point. In turn we call this a poor feed point. Whereby if we locate our feed point in a region of blue or low micromixing values, we can in fact define an optimal above surface anti-solvent feed point. So now let's assess what happens to the local dominant mesomixing timescale. So as we can see from this plot, we in fact notably reduce our dominant mesomixing timescale below the threshold for premature nucleation. So now I pose the question, what impact will this have on supersaturation dispersion and importantly our metastable zone widths and our particle size? So assessing supersaturation dispersion at our liquid surface again, we can see there is an immediate entrainment of concentration or supersaturation to the bulk, and we're no longer facilitating an accumulation of concentration at the liquid surface. So looking at our front cross section here again, we can see the immediate suction due to the intense downward velocities at this point, which facilitates concentration to be dispersed by the impeller almost instantaneously. So now I want to look at our nucleation point and the effect this feed point has on our chord length distributions. Reintroducing the data produced initially at this case study, we can see now at the optimized anti-solvent feed point, we actually now produce the expected correlation of increasing metastable zone with increasing addition rate. Importantly, the nucleation point or metastable zone is extremely robust over the course of 3 experiments with very little statistical error observed. So from this case study we can say that we have understood the effect of turbulent mixing on premature nucleation, and in turn we're able to eliminate this. We also now can predict our metastable zone with respect to anti-solvent addition rate. And finally, I just put in a note here that it's an important factor for controlling particle size and the development of an effective seeding regime. So the system now, from our perspective, is suitable for scale-up. So just looking at some more FBRM here, you can see we're just looking at our mean chord length on the y-axis, and we can see at a poor feed point location we actually decrease our solute mean over time. So after nucleation, the end of nucleation, we can see we just continually reduce our particle size. So we don't grow our particles as a function of time, we reduce them, and that's simply because we continually nucleate out more and more product as we go on through the crystallization. Whereas at the optimized feed point location, we grow our product as a function of time. So again, for maximizing particle dimension and minimizing filtration and drying times, this is obviously the route to go for us. So I say here now at the end, growth is now favored over the entire batch. So back to our presentation overview, and now we'll take a look at case study 2, overcoming poor anti-solvent addition points. So now moving on to case study number 2, overcoming poor anti-solvent addition feed points. On the left hand side here we have an undersaturated solution whereby we add an anti-solvent through a wide feed pipe diameter. As observed here in this video clip, we can observe the sort of premature nucleation of the solute of benzoic acid in this undersaturated environment. If we reduce our feed pipe diameter, we can see here on the right, by increasing the local turbulent kinetic energy by this turbulent jet, we in fact eliminate this premature nucleation. So this increased turbulence created by the jet lowers our meso and micromixing timescales local to the feed pipe. In turn, premature nucleation is eliminated even in this stagnant solution. So I asked the question here, what impact can this have on poor feed point locations in stirred tank reactors? So again, we have to go through the methodology of applying this to our CFD models and then assess nucleation and growth through FBRM. So what is the impact on micromixing and supersaturation dispersion when we reduce our feed pipe diameter? As we can see here on the left in a CFD contour plot of micromixing timescales, we can see that in the plane of the impeller we produce low micromixing timescales, i.e. well mixed, which would be expected, and above this and toward the region of the feed pipe we have in fact large or red values of micromixing, so i.e. poorly mixed. Again, looking at the supersaturation dispersion, the hold up at the liquid surface and then the draw at the region of the impeller shaft, we can see that we actually have a supersaturation pathway that exposes our concentration to regions of large micromixing values. Again, this is going to exacerbate any concentration or supersaturation profiles we have within this bench scale reactor. Now reducing our feed pipe diameter, we can see immediately local to the feed pipe we have in fact reduced our micromixing timescales to those present in the region of the impeller. So now local to the feed pipe our system is in fact well mixed. But importantly, our supersaturation pathway to the bulk is also changed. We now in fact send our supersaturation directly to the region of the impeller, as shown by this annotation. From a simulation perspective, this is far more homogeneous, but we have to quantify this now with the FBRM. So now looking to produce a scalable process that has no premature nucleation and prompts particulate growth. On the y-axis again here we have our metastable zone width, and on the x-axis we have our addition rate in grams per second. Again, noting the premature nucleation events observed with this wider feed pipe diameter. We now reduce our feed pipe diameter, and as we can see, by increasing the local turbulence or by reducing our meso and micromixing values, we in fact eliminate premature nucleation, and produce a repeatable experiment. At 0.3 mil feed pipe diameter, we in fact have an extremely repeatable crystallization with very small statistical error over the course of 3 experiments. So in turn, the increase in turbulence created by the jet of anti-solvent has lowered important meso and micromixing timescales, and this in turn has eliminated the inconsistent metastable zone width and premature nucleation events. So now we produce the expected correlation of increasing metastable zone with increasing addition rate, and importantly we are able to reproduce the nucleation behavior observed at the optimal feed point location. So now we can say the metastable zone is no longer a function of the feed point location, but is a function of the global reactor concentration. So identifying the de-agglomeration of benzoic acid with FBRM and PVM technology. So this slide really demonstrates the power of the combination of the two technologies when troubleshooting strange, FBRM data. So on the y-axis here we have the number of coarse particle counts per second, so that's between 100 and 1000 micron for a 0.78 mil feed pipe. So as we can see here, as we increase the addition rate, we actually increase the number of coarse particle counts observed per second. So I guess I say here a decrease in this trend would be expected from the crystallization or classical crystallization theory. So when we reduce our feed pipe diameter to a 0.3 mil feed pipe, we actually reduce the number of large particle counts per second with an increase in addition rate. So I say here that this is the expected trend. So what actually happens here is this increase in addition rate or increase in coarse particle counts observed is attributed to agglomeration. Whereas with the smaller feed pipe diameter, as shown in the tracer clips, we actually minimize supersaturation, which in turn facilitates the environment for minimizing agglomeration. So the PVM image here on the left shows the agglomerate form produced with the 0.78 mil feed pipe. So you can see this is a cluster of particles, and as you scan this cluster that is agglomerated, you'd actually increase the number of coarse particle counts observed, whereas with the 0.3 mil feed pipe we actually have independent particles. So again, a chord length of these independent particles would produce fewer coarse particle counts per second, hence the de-agglomeration of benzoic acid. I've titled this slide Eliminating Excessive Primary and Secondary Nucleation Events through Reducing Your Feed Pipe Diameter. So on the y-axis here we have our number of fine particle counts, or fine core counts between 1 and 5 micron. We use this size range to classify nucleation, and on the y-axis we have time. So here for our wide feed pipe diameter of 3.2 mil, we can see after about 2.5 minutes we nucleate our product out, but also after about 7 and 10 minutes we also have additional inflection points on our fine particle count trends. This indicates both secondary and tertiary nucleation. So again, this wouldn't be favorable for introducing excessive fine material towards the end of your batch for drying and filtration. Interestingly, after about 13 minutes we have a sudden consumption of our fine particle counts. This was attributed to the agglomeration that was shown on the previous slide. So as we reduce our feed pipe diameter, we in fact reduce the number of fine particle counts per second, but also we reduce our secondary and tertiary nucleation events and agglomeration that was observed in the previous slide. So at the final feed pipe diameter assessed, you can see now we have reduced the nucleation rate, so our nucleation order is reduced, but we've significantly produced a more consistent nucleation event over time. So I can say now the process is now repeatable, even at this hydrodynamically limited feed point. And I have this point here that controlling nucleation behavior through feed pipe diameter will really be essential for this anti-solvent system on scale. So again, going to our presentation overview, let's look at case study 3, developing an optimal anti-solvent addition profile. So within case study 3, we wanted to develop a parallel feed profile which would optimize or maximize our FBRM chord length distributions. Here is a plot of our parallel feed profiles assessed, with our addition volume in grams on the y-axis and time on the x-axis. We assessed a series of parallel feed profiles calculated by this equation, ranging in number from 0.2, which would be a very fast addition at the start of the experiment, to a very slow addition towards the end of the experiment, through to a parallel feed profile of 1, or just simply a constant addition over time, through to a parallel number of 5, which would be very slow at the start and ramps higher addition towards the end of the experiment. So we wanted to assess the impact these profiles had on our chord length distributions at 2 different agitation intensities. One, a very well mixed environment at 475 RPM, and the second experiments were carried out in a less well mixed environment at 325 RPM. So the overall objective being to define a profile which would maximize our FBRM statistics, our median for quantifying our fine material, our FBRM mean statistic for quantifying our average chord length, and finally for characterizing our coarse material we use the FBRM mean square weight. So if we now assess our FBRM median statistic, which quantifies the amount of fine material or small chord lengths present within our system at 475 RPM, we can see it at a parallel number of 0.2. So this is a system which is has a very fast addition at the start of the experiment to a very slow addition at the end. We produce a small FBRM median statistic, which would indicate we produce a lot of fine material. As we increase our parallel number towards a constant addition profile, say for example 0.5 grams per second over the entire course of the experiment, we can see that we notably increase our FBRM median statistic. So from this we can deduce that the increase in the median is due to the reduction in the addition rate at the time of nucleation, so less supersaturation, so less nucleation and more growth. And in turn we can now say that growth is favoured as we make the shift towards this constant addition profile. So now let's look past the constant addition and look at the squared and cubic profiles. So what we can actually see here is after a constant addition profile, we actually reduce our FBRM statistic again, now to values that are less than say 24 micron. So I say here, or I pose the question is the cubic curve not optimal? Like, why do we not continue to grow our chord lengths past this sort of constant addition profile? So let's now break down these experiments and look at some FBRM trends to try really understand what was happening here. So maximizing particle dimension in our well mixed environment at 475 RPM. So we're now going to assess the impact on our median through assessing FBRM trends between 1 and 5 microns. So again, this is the size range we use to characterize our fine material. So if we firstly assess our 0.2 parallel feed profile, so this is a very fast addition at the start of the experiment to a very slow addition rate at the end, we can see we have a high nucleation rate and we produce quite a lot of fine particle counts or chord length counts per second. Now moving towards a constant addition profile which observed a larger median, we can see that we notably reduce our nucleation rate and importantly reduce the amount of fine material produced over the entire batch of the experiment. Now moving to a parallel number of 5.0, we can see again we reduce the nucleation rate, but after a time of approximately 40 minutes we actually induce secondary nucleation. So this in turn increases the amount of fine particle counts observed per second, which in turn facilitates this reduction observed in the previous slide of our FBRM median. So I can state here that, however, additional nucleation events with parallel numbers greater than 1.0, due to the increase in addition rate towards the end of the experiment, reduces the system's particle dimension. So from this sort of analysis, FBRM analysis, we can deduce that in a well-mixed environment over the course of a 1 hour experiment, a simple constant addition profile will maximize FBRM particle dimension. So now looking at our less well-mixed environment at 325 RPM, again looking at the same FBRM size range on our y-axis between 1 and 5 micron and time on our x-axis, we can see with the constant addition profile, in this case we actually have a high nucleation rate and an increase in the amount of fine material produced. Moving now So now let's use some FBRM trended statistics to quantify the shift in the optimal profile observed at 325 RPM. So looking at our FBRM mean between 1 and 1000 micron here on our y-axis and time on our x-axis, we can see as we change our power law feed profile from a simple constant addition to a squared addition profile, we actually observe an increase in our average chord length over the entire course of the experiment. Now quantifying the coarse end of our distribution, so our FBRM mean square weight, we can actually see that we also increase the coarse end of our distribution, or the mean square weight statistic, again for the entire course of the experiment. So from this analysis we can deduce that the reduction in mixing capabilities observed with the reduction in agitation intensity from 475 to 325 RPM, well, this can be really managed by the application of squared power law feed profiles for the experimental time assessed in this case study. So overall from this study we can really say that the application of these sort of power law feed profiles on scale up, where typically we observe a decrease in mixing efficiency, it will really be essential for controlling or maintaining a particle dimension on scale and in a scale down environment. So now summarizing this case study, we can see here with feed volume on our y-axis and time on our x-axis that in a well-mixed environment at 475 RPM, simple constant addition, i.e. 0.5 grams per second, maximizes our FBRM median, mean and mean square weight. And for a reduced mixed environment at 325 RPM, the profile is required to shift to a squared profile. This profile combats the effects of poor mixing by reducing supersaturation at the time of nucleation. This in turn facilitates a minimal nucleation event, which in turn allows for the CLDs or particle dimension to be maximized. So finally, just to some acknowledgements, I'd like to thank you all for attending this webinar. And secondly, I'd like to thank my colleagues within the UCD Crystallization Research Group and within the Solid State Pharmaceutical Cluster, with particular reference to Professor Brian Glennon and Professor Kieran Hodna for allowing me to present this material today. And also to Des O'Grady and Brian O'Sullivan for really helping me out a lot throughout my PhD. And to Ben and Rule for making this webinar happen. So at this point, I'd like to stop and love to take any questions. I have my email there, and also the UCD website if you'd like to attain more information about our PAT crystallization training and research programs.